All right, so if you notice on a web work, there is no section for chapter 4. That's weird. So I just realized that, and then I was like, oh, okay, so you will be doing the textbook problems for chapter 4 materials, and there's also no whatever that thing, the web work. There's no assignments for 5.1 and 5.3. I think those are the section. So the EC4, I don't know what that's about. I didn't open it. Sadia, do you know if that's related to chapter 4? So, yeah, we'll double check that later. I can also check it after class too. But as far as I saw, there was nothing titled 4.2 or 4.3. So I would strongly encourage you to do the textbook question to practice section 4.2 and 4.3, and you can also look it up 4.1 as well. So those are from the textbook. And chapter 5, 5.1 and 5.3, that's also going to be from the textbook. So do the recommended question. I think they're nice. They're probably the best questions too. All right, so any questions? Okay, so you guys are welcome to use your audio. I'm gonna start writing so that way I don't need to keep flipping back and forth. Let's see how this goes. Okay, so let's start with so let's finish up 4.2. That's what we were doing last time. So just to rewrite it one more time. So for web work, um, no. So let me start off by writing it this way. So for sections 4.2, 4.3, and then 5.1, 5.3, use the recommended textbook questions. Okay, so you won't see any assignments on that, I believe. I didn't see it, but if I see it, I'll open it up. Just in case you want practice, which you should do, you will be using the textbook for these 4 sections. And then as we go along, I'll check which other ones we don't have. Notify you guys as we go along. So Sadia just checked EC4 has linear algebra stuff. So you can ignore that part. I wouldn't bother. If you want to look, do it, do it. I wouldn't worry about that. But you can go ahead and learn more materials on your own. So you were to judge. Okay, so let's start with where we left off last time. So we started talking about higher order differential equations. So let's continue with that. So we are currently on section 4.3, finishing up. No, sorry, 4.2. Sorry, I'm probably going to make mistakes today again. So if you see something is weird, let me know. Okay, so you can speak through your audio. 4.2, continue from last time. So we're working with L of y, which is an nth order differential equation. So I think the notation I gave you yesterday was a sub 0 y to the nth derivative plus a sub 1 y to the n minus 1 derivative plus all the way up to a sub n minus 1 y to the first derivative plus the constant term a sub n y equals to 0. So we're working with nth order differential equations with constant coefficient homogeneous. So all these a0, a1, all the way up to an, they represent the constant coefficient, so they're real valued, and y to the nth represent the derivative, okay? And we assume that the solution has the exponential form. So solution form, we said it's going to be the usual y equals e to the rt, And then from here, we had to figure out what are the possible roots for r. And from there, you can write out the different form of solutions. If it's distinct real, we know how to write that. If it's real repeated, we also know how to write those. And if it's complex, we know how to write those as well. So we have learned that in chapter 3. So, okay. So now we talked about the method to solve nth order polynomial. So the characteristic is going to be a polynomial. So we said to find root to the nth degree characteristic polynomial, we have several methods, but the one method that I encourage you to always try with is factoring, because that's the simplest method. So factoring will be nice if we could factor. If you can't factor, so if you're unable to, then we have the rational root test. So we talked about that last time. We have a rational root test. That would be the second option. And then within the rational root test, once you figure out the possible root, we know that we can do either plug in into the original characteristic equation, or we can do synthetic division. Or if you want to do long division, you can do that, but I wouldn't recommend long division because synthetic division works just fine. So why not, right? We want to use up the least time as possible and speed up the computation. So I would go with synthetic division. And then if the roots are complex, then we can't really do rational root test because it's for rational. So we have another method. So we always have alternative. So the third method we started discussing was the roots of unity. Okay. And roots of unity it will give us complex and real root. So it's a very powerful tool, but it has a very specific form. So you can't really use it all the time. So all of these methods are very specific, okay? But they're all options, so they're good. So here's when we're going to use roots of unity. So let's illustrate number 3. So let me know if you guys have questions while I continue. So let's illustrate number 3. So we want to know, how do we use roots of unity? So if you guys remember, roots of unity is a way to express a complex number in polar form, okay? So let z be a complex number, so a complex number, which means we can express z as a plus bi. I know I use alpha and beta. I'm using a and b right now. They're just numbers, okay? So don't get confused by me switching them around. It's okay to switch them around as long as you give meaning to them. So where a and b are real numbers, okay, that's what the little e means. And imaginary part will be the I, right? And we want to write, so we want to express this complex number z in polar form. That's the idea, okay? So polar form. Well, what does it mean to have a polar form? It means if you have z as a complex number, which is a plus bi, we want to write this as r times e to the I theta, where r is the magnitude of that complex number. So r is the magnitude which can be defined as the absolute value of r. And we know from, sorry, not absolute value of r, absolute value of z. So first mistake, sorry. Which means from calculus, you know magnitude means you take the square root of all the entries. So the entries are a and b. So we have the square root of a squared plus b squared. So that's how we define r, the magnitude of z. And theta is the angle. So theta is the angle, so it's going to be defined as tangent inverse of b over a. So you can think of it this way. In pre-calculus, you studied to find an angle, you have to do inverse function, right? So if it was a sine and you're looking for an angle, you do sine inverse. If you're looking for cosine, you do cosine inverse. Similarly, here we're doing tangent inverse. You will see why. In a few minutes, you will see it. So how do we use this? So let's consider an example. So let's consider the following. If you have z to the nth power is equal to a number. For simplicity, I'm going to use 1. Okay, it could be any number, really. It could be 2, it could be 4. 1 is just nice, that's why. So the solution is called roots of unity. So the reason we give the name unity is because the number z to the n is equal to 1. 1 is unity, okay? But it could be any number, really. So how do we use this? So let me show you how to use this. So if I were to give you a complex number, and then we'll tie all of this into differential equations. So let's just consider a simple example. So let's express 1 as a polar form. Okay, so let's express this number 1 as a polar form. So we're going to draw it. We're going to learn how to draw a complex number. So 1, I can write it as a complex number. So we have 1. So the number we're looking at is z is 1 plus 0i, right? That's a complex number. So where your a is 1, then your b is 0. Okay? So let's draw this. So if you remember from your homework assignments, I'm not sure if this was one of the questions, the x-axis is the real axis, the y-axis is the complex axis. Okay? So you have the real numbers 1, 2, and so on, and then -1, -2, and so on. And on the y-axis, you have the complex numbers. So you have 1i, 2i, 3i, and so on. And on the bottom, we have the negative I, negative 2i, and so on. Hopefully you got the idea. So I want to draw 1, 0i. Well, so in y direction, it's 0. In x direction, it's 1. So we have, so from the origin, this point is located right here. That's the complex number 1 plus 0i. Okay? So I shouldn't draw it like that. Sorry guys. I should draw it this way. That's the point. And that's the direction, okay? So we want to know what is r, meaning the magnitude of this. You can think of it as a vector if you want to. Magnitude of this complex number. And what is the angle, okay? So let's determine those. So we know z is going to be r e to the I theta. Okay, so I'm going to go ahead and rewrite. So we know r is the magnitude of z, and that's determined by a squared plus b squared. So in this case, a is 1, b is 0, so it's just 1 plus 0, that's 1. So our radial distance from the origin is 1. So that's this distance right here, 1. So r is 1. now we need to figure out what is theta. Well, theta is angular, right? So what's the angle at this location? 1. Can someone tell me the angle? 0, right? So if you think of it as a pre-calculus question, you would say the angle is 0 degree or 0 radian. So theta, you can always get it from the picture, that's 0. Or if you want to strictly use the definition, so that would be tangent inverse of b over a, right? So that would be 0 over 1, which is tangent inverse of 0. And luckily we know pre-calculus, this is 0. Okay, so we have 1 e to the I theta. Theta is 0. Okay, so this is going to be weird. 0 plus, now if, so maybe I should explain it this way. 0, okay. So really this is just 1 because e to the 0i is just 1. So in polar form, 1 is also 1, so it doesn't really do much, but the idea is still explained. But if you think about it, if you want to look at every rotation, meaning every revolution of this, and you make it into nth power, that means there's going to be a solution in every period, okay? So what we often do is we would write it as, so r. You can do e to the I 0 plus the period, which is 2 pi. So we'll do 2n pi, where n is integers. So if we were to look for solutions, we would tag in that 2n pi so that we can let n run up to the power of z to the n, 1 minus n, okay? So I hope that makes sense. But for this question, the answer would just be this, because we're looking for specifically how to express the number 1. Let me do another one, and then we'll do how to do z to the nth power. So let me know if you guys have questions. So let's do -1. So in polar form. Okay. So let's do the same thing. We rewrite z, some value z is equal to -1 plus 0i, and I want to express this as r I theta. So let's draw the picture, because the picture really gives you what theta is, okay? So let's draw. So -1 and 0i. So this is the real line, and this is the complex line. -1 is located right here, and 0i, so the point we're looking at is this point right here. That's what we're looking at. So we want to know r, what's the distance from the origin. So r is going to be this piece. That's r, the distance from the origin. Theta, it's gonna be from standard position going all the way to the terminal side. So you're gonna start from standard position right here, and you go all the way to the number -1. That's your theta. Okay, so I hope that makes sense. Now let's figure those out. So what is r? Well, we know by definition r is the magnitude of z, which is square root of a squared plus b squared. So by looking at the picture, what's the distance from 0 to -1? 1. So we know r is 1. And what is theta? By looking at the picture, what is theta? 180, right? So you can say, so we're going to use radians because it's simpler. So theta is going to be pi. So now let's write it in polar form. So therefore, z is equal to -1 plus 0i. In polar form, we have r e to the I theta. Plug in those values. R is 1, e to the I theta Well, theta is pi. But we want to look at every single value for this. So this is rotational, so it's just going to repeat itself again, go around and then come back here. So that will be plus 2n pi. So that would be the expression for -1. Okay, so let's do another example. What about if you want to express 1 plus I in polar form? So I'll give you guys a few seconds to write it out. So again, I'll encourage you to draw the picture. It's so much better when you draw it. Okay, so let's start. So let's draw this. So we want to draw z, which is 1 plus I. So here is our real line. Here is the complex line. So in x direction we go 1 unit. In y direction we also go 1 unit because I is 1. So we have 1 and I. So the point we're looking at is this magical point right here. So r is this distance, and theta, it's going to be this angle right here. So the red is theta. So red is theta. So tiny. Don't know how to indicate that. So so that's theta. Okay. All right. So let's find those pieces. So we want z, magnitude of z. Z is 1 plus I. So r is going to be, so we want to write this as r e to the I theta. R is going to be magnitude of z, which is square root of a squared plus b squared. So so what's the magnitude of this complex number? Yeah, right. So this is 1 plus 1 square root of 2. And then theta. What's theta in this case? What is that angle? Right. So so this would be right. So pi over 4, 45. Okay. So in complex form, we have 1 plus I is equal to r e to the I theta, which would be, so we just figured that out, and I'm not writing, e to the I pi over 4. And then sorry, not 2, 4. And if you want all of them, you just write plus 2 and pi, where n is a multiple, integer multiple. So that would be the polar form of 1 plus I. Now let's take this into differential equations, and let me show you how to use it. So here's what you're going to be tested on in this course, something, a very nice method to use. So let's solve y double prime plus y equals to 0. Triple prime, third derivative. So we know we can write the characteristic polynomial of this. So we have r cubed plus 1 equals to 0. So here you want to think of r is your z. Okay, so this is what you're going to do. You're going to say, okay, let's solve for r cubed. So we have r cubed is equal to -1. And this is the number you want to express in complex form. Okay, so -1, if you were to express it in complex form, we want to write this as r e to the I theta. So whereas before we used the number z, but you're really using r to be your z. So back of your head, you should be thinking r is z, okay? So we want to know what are the possible value for r and theta. So in complex form, we know -1, we computed that like a few seconds ago, that's right here. -1 plus 0I is going to be right here, e to the I pi, and then plus 2n pi for the periodic concept, right? So this is same as writing 1 e to the I pi plus 2n pi. So that's the polar form of -1. So what do we have really? So what we really have is r cubed is equal to e to the I pi plus 2n pi. Okay? Well, we don't want r cubed, we want to solve for r. So we want to get rid of that 3 by taking cube root. So I'm going to go ahead and take cube root, so raise it to 1/3 on both sides. So then we have r as our root, which is equal to e to the I times pi over 3 plus 2n pi over 3. So that's where r is equal to. Now, how far are we going to let n run? Well, n can run all the way up to infinity, right? But to save time, that's what we like to do, n will start from 0, 1, and 2, okay? And we're not letting it run any further because once it hits 3, it's going to start recycling the same solution, same value for r, okay? So beyond 2 for this problem, so beyond 2, it will just repeat, okay? So in general, think of it this way. So always let so and run from 0, 1, 2, all the way up to um, up to 1 less than the power of the polynomial. So here you see how you have r cubed equals -1. So that means you're only going to run from 0, 1, 2 because that's already 3 roots, right? So 3 possible values for r. So I would say run up to 0, 1, 2, 3 up to m minus 1, meaning 1 degree less. 1 degree less than the power of the characteristic polynomial. So let me know if that makes sense. Does that make sense, guys, what I'm talking about? Okay, so this will give us the three roots. So we have r1, r2, r3. So 0, 1, 2, so that's the 10th, the third degree for r. So now let's figure out what are the possible roots, right? So 1. So r1 is going to be, we're going to let n to be 0. So r1, we're going to find this by letting n equal 0. So if n is equal to 0, we have r1 is equal to e to the I pi over 3, 2 times n pi over 3, that's going to be 0, so it's just pi over 3. Well, that's a root, right? But we know how to do better. We know how to do better than this. We know how to use Euler's identity. That's what we covered previously. So using Euler's identity, this is cosine of pi over 3 plus I sine of pi over 3. So this is by Euler's identity. So make sure you remember Euler's identity from the past, okay? And now here you just want to evaluate, what is cosine of pi over 3? So if you remember from 1/2, right? Thank you. And then we have plus I. What's sine of pi over 3? Square root 3 over 2. So we have R1. There you go. It's a complex root. Okay? Now, here's the nice thing about complex roots. If you know one of the root, you know another one is also a root, meaning it's conjugate. So if I know that's R1, then I can just say R2 is going to be 1/2 minus I square root of 3. So that's the best thing about complex number. If you know one, you know the second one as well. So we have found 1 and 2. Now we just need to go for one more root, and then we have the general solution to write out. Okay? So for the next one, I'm just going to go down the list, start with n equals 1 now. So now to find another root, because we need another one, let's call it R3, because we already found R2. Let's pick n to be 1. Hopefully it doesn't give us the one we just guessed, but let's see. So we're going to have e to the I pi over 3 plus, now n is 1, so we're going to get, what are we going to get? So 2 pi over 3, right? So I'm plugging in n values, if you're not following right here. That's where I'm plugging in the n values and then evaluating using Euler's identity. Okay, so here I can combine before applying Euler's identity. We have e to the I, so 2 pi plus pi, that's 3 pi, so that's just pi. Okay, and by using Euler's identity, we have cosine pi plus I sine of pi. And now we evaluate what is cosine of pi. Okay, so this is -1, and then sine of pi is 0. So we have our third root that we wanted. Now if you go ahead and test for n equals 2, that was the last choice we had, you're going to get 1/2 minus I square root of 3 over 2. So that we already have that, so we don't have to go and bother. So no need to do. So no need to do n equals 2 since we have all roots. Okay. And then you can also test it out for yourself. If you pick n to be 3, then you'll see that these three solutions, these three roots that you found, they're just going to repeat again. So you don't have to keep going because you're going to be wasting a lot of time. So we can just stop once we have the number of roots we wanted. So we have one real root and we have two complex roots. So let's write out the solution. So our general solution to this problem, so the general solution, it's going to be y equals C1. So I'm going to use R3 first because it's nice. That's why. That's the only reason. Plus, now the next two is going to be the cosine and sine. So we have C2. So we have, okay, C2 e to the 1/2 t cosine of square root of 3 over 2t plus C3 e to the 1/2 t sine of square root of 3 over 2t. And that's our general solution. So any questions? Any questions on this method? Okay, let's do another one. Let's see. So the reason you can't always use this because this only works if you have this form where you have you can use this when you have this form right here where you have just on the left side you have r to some power equals to a number. But if you have more than one term on the left side, then you can't really use it, right? So that's why here we have r cubed right here is equal to 1. So we subtract 1, we have r cubed equals to -1. So it's in the specific form we want it. That's where we're able to use it. So we're expressing 1 as a complex polar form, and then from there we can just find all the possible values for r. But if you don't have it in this form, if you have, like, say, another term right here, r squared, well, we can't really do it, right? We don't have a rule for that. So we go with other approaches. Okay. All right. So that's that. Let's do another one. So let's solve. So let's compute the general solution for y to the fourth derivative plus y equals to 0. So let's start. So we have r to the fourth plus 1 equals to 0. So we know this can be written as r to the fourth equals to -1. So the exact same form we wanted. We wanted to, so think of it, z to some power n equals to, a number. Some alpha, a number, right? If it's in that form, then we can use the root of unity rule. So we can use it now. So this is what you're thinking, right? So that means I want to express -1 in polar form, so that's -1 plus I, sorry, not I, -1 plus 0I. We want to write this as r e to the I theta. So again, you can draw it. -1 is located right here, and in the y direction it's 0. So this is theta, and r is this distance right here. So that's r, and that's theta. So we know from before, r is 1, theta is pi. And we want periodic solution, so 2n pi. Okay? So let's write it out. So we have r to the fourth is equal to 1 e to the I pi plus 2n pi. And we want to solve for r by taking the fourth root. So we have r is equal to e to the I times pi over 4 plus 2n pi over 4. And then the second half I can simplify. This is just e to the I times pi over 4. Actually, I'm not going to simplify. You'll see why in a few seconds. So let's not simplify. Okay. So let's just keep it as it is, because you'll see why. Okay, so we'll keep it right here. Now, how far are we going to let n run up to? Alright, so it's going to be 0, 1, 2, and 3. Because your m that you're thinking is 4, so 4 minus 1 would be 3. So let's find the possible roots. So if n equals so why don't you guys go ahead and find values for r. I'll give you guys a few seconds. Okay, so hopefully you had some time to come up with some values for r. So let's see. So if n is equal to 0, let's call it r1. That's going to be e to the I. So n is 0, so the second term will disappear from the exponent. So it's just pi over 4. Now we can apply Euler's identity. So we have cosine of pi over 4 plus I sine of pi over 4. Okay, so what is that going to give us? Well, we know cosine of pi over 4 is root 2 over 2 plus I sine of pi over 4 is also root 2 over 2, so that's nice. Alright, so we know R1, that's square root of 2 over 2 plus I square root of 2 over 2. Well, if that's a root, then we know its conjugate is also a root, right? So that means we can say that we know another root to this. We know R2, which is the conjugate of this, that's square root of 2 over 2 minus I square root of 2 over 2. So we know 2 of them, so we need 2 more to go. So that's nice. So let's hope the next one is also complex, so we can just use its conjugate to be the fourth root. So let's get excited. So let me pick n to be 1, so I can find another root. Let's call it R3. So plugging in n equals 1, we have e to the I pi over 4 plus, so n is 1, so we have 2 pi over 4, which would be e to the I 3 pi over 4. Okay, so let's see. So using Euler's identity, this would be cosine of 3 pi over 4 plus I sine of 3 pi over 4. And now you need to evaluate these. What's cosine of 3 pi over 4? Okay. And sine of 3 pi over 4. Okay, so that's positive. Well, so we're happy because we got a complex root as the third value for r. So that means its conjugate is also a root. So we know r4, it's going to be negative 1 square root of 2 over 2 minus I square root of 2 over 2. So we have all the roots we wanted, and they all happen to be complex. And that's fine, right? We know how to write solutions. So let's write the solutions for R1 and R2. So our general solution is going to be y equals, so I'm using R1 and R2, C1 e to the square root of 2 over 2t cosine of square root of 2 over 2t plus C2 e to the square root of 2 over 2t sine of square root of 2 over 2t. So that's the complex conjugate of R1 and R2. That's how the solution looks like for those two. And then the next two, R3 and 4, would give us C3 e to the negative square root of 2 over 2t cosine of square root of 2 over 2t plus C4 e to the minus square root of 2 over 2t times sine of square root of 2 over 2t. And there you go. That's our magical solution. So, any questions on this? Pretty cool, right? You just gotta do some work, but they're nice. Okay, so any questions on this? Alright, so if there are no questions, let's tag in the non-homogeneous portion to this, okay? So that's going to be 4.3. So we found the solution to the homogeneous. Now what if we want to compute the non-homogeneous, right? So we need to learn how to do those. So moving on to 4.3. So section 4.3. So 4.3 will do the method of undetermined coefficients. For higher order. So this is for higher order. Okay. So everything that we did for second order, now you just extend it to higher order. So the idea still carries. When do we use method of undetermined coefficient? Well, when g of t, so what are the cases, guys? When g of t is what? So polynomial, what else? So if it's a combination of polynomial and exponential. And the last case is if it's polynomial and exponential and sine or cosine. Right. So these are the three cases when we use the method of undetermined coefficient. So let's look at it. So let's look at a non-homogeneous case. So suppose we want to compute the particular solution, the form of the particular solution, and maybe I'll solve one question. You can see how much time these will take us, but we can still do it. So let's do one full example. So find the general solution of the differential equation y to the third derivative minus 3y double prime plus 3y prime minus y equals to 4e to the negative t. So you see this is non-homogeneous because on the right side we have a function of t, okay? And it's an exponential, so we're going to be using the method of undetermined coefficient. So let's take a deep breath and then we'll start. we'll start in a few seconds. Okay, so let's get started with this. So we wanna first, so if you remember, hopefully you remember that to use the method of undetermined coefficient, first we need to find the solution to the homogeneous, right? So let's find YH. So we write out its characteristic polynomial. So we have r cubed minus 3r squared plus 3r minus 1 equals to 0. So just double check my work. I think I have it right. Okay. Well, how do we... So what technique are we going to use here? So it looks like you can factor this, right? Let's think about this. So Sadia says r minus 1 cube. Yeah, it looks right. That looks right. R minus 1 cube equals 0. Okay, so we have r is equal to 1. And this is repeated 3 times. Right? So we have r1, r2, r3 equals to 1. So our YH is going to be C1 e to the t plus C2 t e to the t the next one is also repeated, so to make it distinct from the first and second solutions, we put a t squared, e to the t, c3. So these are the homogeneous solutions. Well, now we need to guess the form of the particular solution. So yp. So someone tell me, what's your guess for yp? So what do we multiply by t for this one? So let's think, right? Do we need to multiply it by t? Okay, good. So you corrected it. All right. So not in trouble. We got it. So Sadia, you also have it too. So because the exponent is different from the homogeneous solution, there's no need to modify the yp that we're guessing. So this is the right guess for yp. Now, so we need to compute its first derivative, second derivative, and third derivative. Plug everything into the original because that's what the original looks like. So let's do that. So if yp is that, yp prime, so we have yp prime, that's going to be negative a e to the negative t. So this is not so bad, right? We can differentiate exponential as many times we want, so this is okay. Y double prime of p, that's a e to the negative t, and the last one, yp triple prime, that's going to be negative a e to the negative t. Not so bad, we can manage. Now let's plug them in. So now plug in yp, yp prime, yp double prime, yp third derivative into the original. Okay, so if we do that, we have y to the third derivative, so that's negative a e to the negative t minus 3 y second derivative, so that's going to be a e to the negative t. And then we have plus 3y prime, so plus 3y prime, so that has a negative from the derivative itself, so this would be minus. So negative 3a e to the negative t, and the last term is just minus y, so that's minus a e to the negative t. Everything equals to 4 e to the negative t. Alright, so that was a success. Okay, and now we want to equate the coefficients, so they all have e to the negative t in common, and they all have a, so I can kind of put them all together, right? So we have negative a, so negative 3a, negative 3a, that's negative 6a, and the negative a, that's negative 7, and the last one, 8. So we have negative 8a is equal to e to the negative t is equal to 4 e to the negative t. Just making sure I did it correctly. So now we equate the coefficients. So 8a is equal to 4, sorry, negative, which means a is equal to negative 1/2. That wasn't so bad. So we got it. So our general solution, so y is equal to the homogeneous solution plus the particular solution. So we have yh, which was the solution we computed earlier, c1 e to the t plus c2 t e to the t plus c3 t squared e to the t, and yp is negative 1/2, that's a, e to the negative t. So that would be our solution.
Let me know if you guys have questions. Any questions on this? Okay, does it make sense?
Okay, so the higher order, they're just the extension of second order and what we did so far. The idea is the same. It's just maybe the period where you should spend more time is the characteristic polynomial, because you want to think about what are the possible roots for R and how do we get them. Okay, so I would encourage you to practice factoring as much as you can. And maybe synthetic division is nice too, so you can use that, which is fall into the rational root test steps we had. Okay, so let's do another one. So before I move on to another one, here are two more formulas that it might be useful for you if you want to consider them. So here's some useful formulas. So we have sum of two cubes. So if you have a plus b cubed, this would be a cubed plus 3a squared b plus 3ab squared plus b cubed. So this is also useful. So if you see the right side in any of your equation, you can always kind of match them up so it looks like a plus b altogether cubed. Another one that's also useful is the one we just used, was a minus b cubed. And this would be a cubed minus 3a squared b plus 3ab squared minus b cubed. So these two formulas are useful sometimes. Okay, so they're always good to know them. Okay, so let's do another example. So for this problem, we want to just determine the form of the particular solution, but we're not going to solve for the unknown coefficients because it will take us a while to really solve it if g of t involve more than one function. So here's an example. Let's just find the particular solution. Okay, so let's say you have y to the third derivative minus 4y prime is equal to t plus 3 cosine t plus e to the negative 2t. So you see how your g of t here happens to be three different functions. So solving for the general solution and determining all the unknown coefficients, that will take us a while, right? Probably good 2 hours. Maybe not, maybe 1 hour. But the idea is know how to set it up, and then we'll worry about solving the undetermined coefficient maybe in the future using computer system. But for this course, we just want to determine what will be the possible particular solution. So let's focus on that. Well, in order for us to do that, we need to first compute what is the homogeneous solution. So let's find YH. Okay, so we write out its homogeneous equation, and then we write its characteristic polynomial. So we have r to the third power minus 4r is equal to 0. So how would you find the roots to this polynomial? So we have r times r squared minus 4 equals to 0. And then r squared minus 4, you should notice it's also factorable. So we have r times r plus 2, r minus 2 equals 0. So we have all the roots we want, so that's good. R1 is 0, R2 is negative 2, R3 is 2. Okay, so we have real and distinct. So we know how to write out the solution to this. YH is going to be C1 e to the 0 plus C2 e to the negative 2 plus C3
e to the 2t. So that's our homogeneous solution. Okay. So now we're going to determine the form of our particular solution. So I'm going to go ahead and start labeling g of t as yp1, yp2, yp3 because we have more than one function for g of t. So let's label this one as yp1. Okay. So let's call this one yp1, this one yp2, this one yp3. And then our particular solution will be the combination of yp1, yp2, yp3. I hope that makes sense. So let's figure these out. So what's yp1? What's the form of yp1? So it looks like it's a first degree polynomial, so it's a t plus b. Now, does any of these overlap with my homogeneous solution? It does, right? B is the trouble. So we need to modify this entire piece by what? So what will be the power of t that we can multiply by to make it independent from the homogeneous solutions? T. Okay, good. So both of you said it at the same time. T. Well, now let's do yp2. So yp1 is good. Let's do the second particular solution. So we're looking at 3 cosine t. Okay, what's the particular solution form for that one? Okay, now do they overlap with the homogeneous? Nope, so we're good. Last one, yp3. What's the form for this one? Okay, now, so we multiply by what? T, and that will do the job. Okay, so let's write out our particular solution. So our particular solution, which we're calling y sub p, that's going to be yp1 plus yp2 and yp3. So we have a t squared plus bt plus c cosine t plus d sine of t plus, so it looks like I'm writing straight, but I'm not. Sorry guys. It's like tilting upward toward the sky. E to the negative 2t. Okay, it's a little tilted, but you can still read it, so I'll try to write straight next time. So any questions on this? So I can't really draw a box, like a small one, because it's tilted, but so there we have our particular solution. Now we can imagine how much work it's going to take us to solve for these undetermined coefficients. A, B, C, and D, and E. We'll be computing 3 derivatives and then plugging everything in, equating the coefficient. So it's a good homework question, but its solving part would not be a good test question. So know how to set it up, okay? That's something I can test you on. Setting it up, finding the particular solution. So any questions on this concept? So let me do another one. So here's another example. So here's another example we can do. So again, I'm not going to finish the problem because I think you can finish the algebra, right? Find the general solution. So I'll start you off with this problem, but you can finish it up when you have time, right on the weekend. We have, what, 4 days weekend? So we don't see each other until Tuesday, so why not, right? So, so let's do y to the third derivative minus y to the second derivative minus y prime plus y equals to 2e to the negative t plus 3. Okay? Okay, so something like this we can solve because g of t doesn't involve much, but it's enough for us to determine what the function would be for the particular solution. Okay, so let's write out the homogeneous solution to this. So we have YH, so we write out its characteristic polynomial, r cubed minus r squared minus r plus 1 equals to 0. Okay, now this one doesn't look like any of the formulas that we've seen, so I'm going to go with factor by grouping. Okay, so we can factor this by grouping. So let's see. So I'm going to group the first two. You pull out the GCF, and then you have r minus 1. And the second one, I'm going to pull out a negative 1. So we have r minus 1 equals 0. And then I'm going to factor out r minus 1 from both. So we have r squared minus 1 equals to 0. And I can factor r squared minus 1 again. So we have r minus 1 times r minus 1, r plus 1 equals to 0. And I see that r minus 1 are repeated, so this is r minus 1 squared, r plus 1 equals to 0. So we have our root. We have r1 is equal to r2, which is 1, and we have r3, which is negative 1. So here are the real roots. One of them is distinct, another one is repeated. So YH is going to be C1 e to the t plus C2 t e to the t. So that's with the repeated root, R1 and R2. And R3 will give us C3 e to the negative t. Alright, so we have our YH. So that's our homogeneous solution. Now let's determine the form of the particular solution. And then you'll finish up the question at home. Well, you are all home, I'm hoping. For homework, you will finish it up. So that's for you to exercise some algebra muscles. So let's do this. So again, I have two functions. So you can think of this as yp1 and this constant as yp2. So we have two different forms for the particular solution. So what is yp1? What's the form of that? Okay, so let's see if it overlaps. It does, right? So how do we modify? Good. So that's yp1. What about yp2? So that's the constant. What's a particular solution form for a constant? Yeah. And does this... No, it doesn't give us trouble, right? So it's already independent. Okay, so we have our particular solution. Yp is equal to at e to the negative t plus b. And then from here you can go ahead and take its derivative, plug everything in, you will be able to find a and b. So finish me. So that's for you to do over the weekend. Okay. Alright, so any questions on this method? That's pretty much all for 4.3. Just working with more non-homogeneous case for higher order. That way you can determine its particular solution. Sometime you'll solve for these undetermined coefficients, sometime you wouldn't, so just know how to set them up. Okay, how do you guys feel? okay? Right, I'm gonna take that as a okay. All right, so okay, so that will conclude chapter 4. Okay, moving on to chapter 5. So chapter 5, so we're gonna study chapter 5 in depth because we will be working with power series solutions. Very exciting stuff. So if you need to brush up on your power series skills, it's the time to review calculus. So if you need to review those, use the weekend to review, or whenever you have time, just review. So make sure you know power series just a little bit, not too much, because we're going to go over it in class. Just have the basic idea with power series, okay? So let me do a brief review on power series, and then we'll start with the solutions using power series, the differential equations solution in a form of power series. So it's a very nice way of expressing solutions, and you'll see the magic of it as we do these problems. But it's also heavy in algebra again. So not to scare you off, but to tell you, give you a heads up, hey, start working hard so that when we actually do solutions, probably tomorrow, you wouldn't fall behind or you won't feel lost. So chapter 5 is titled, I think it's called Power Series Solutions. Yep, so series solutions. Of second order. Linear equations. So we're going to work on power series solution for only second order, so no need to worry about higher order, but it works, okay? You can also do it for higher order, it's just it's long. So second order is good enough. So 5.1, it's not much of the material for this course, but it's good to understand a little bit about power series, little bit of review of power series so that we're familiar with how they look like, and then when we're seeking the solution as a power series form, you know what they are. So 5.1 is a review of power series. Okay. So what's a series, right? Let's define that. So here is a definition. A series, AN, if you remember, is sum of all terms, right? Sum of, say, first n terms, or you can have infinite sum, right? So infinite sum as well. So let's keep it finite, is the sum of nth terms in a sequence. Sequence is just list of numbers, whereas series, you sum of the list. Okay, that's the difference between the two. So here's a notation that you should have seen already, or if you haven't, I would say review just a little bit. So we have this sigma, which is the summation, we call it. This is the starting point, n equals 0, and this is the endpoint, infinity, so meaning it doesn't end, it's just keep going. So this is the infinite sum of an. So if I were to write out sum of the term of this infinite sum, I'll let n run from 0, 1, 2, 3, all the integer, okay? So you'll have a0 plus a1 plus a2 plus so on. So that means it's just keep going. So this is what we call an infinite sum. Whereas this is the starting point, and this kind of like the end point. So see, I don't want to say endpoints because it's infinity, but think of it if it was finite, which will be the second example, second notation I'm going to give you. So suppose your summation looks like this, starting from, say, some n equals 0 to k, where k is some finite value. So you have a sub n, so you'll have a0 plus a1 plus a2 all the way up to a sub k, which is the last term of this series. So it terminates at k, and this is what we call a finite sum. Finite just means it stops at some point, okay? So you could have, for example, n equals 0 to 5. So you would do 0, 1, 2, 3, 4, 5. It terminates after 5. So you can think of this as the, let's call this upper limit. I wouldn't say terminate, so upper limit is a better word for this. And the bottom will be a starting point of the index. Okay, so these are just some common terms that you should have already seen in calculus when you did power series. Okay, have you guys seen this? Does this look familiar? Long time ago? Okay, so for some of you it looks familiar, for some of you it's been a while. That's okay, I think you can always pick up with a little bit of review, so I would encourage you to do that. Now, series, they also have some properties, right? So let's go over just the major one. I'm not going to go over the entire session on power series because we don't need a lot of it. We just need some of it. So what are some useful properties of power series? So properties of series. So if you have, say, so one, if you have a sum, so this is the one we're going to be using for this course, that's why I'm going over this. If you have a sum starting from 0 to infinity of an plus a sum starting at same n equals 0 to infinity, so you have two different sums, but they start at the same point and they're both infinite. So call it a bn, right? You're allowed to join them into a single summation. So that's one of the property. Very powerful. So we can do sum from n equals 0 to infinity of an plus bn. Okay, so we're allowed to do this as long as they start at the same point, meaning their starting point is the same and their end point is also the same. So they're just same summation but different sequence. You can think of it that way. We can also subtract them. That's also valid, okay? So the same rule would apply for addition and subtraction. So this is very useful identity or property we're going to be using in the future. Now the second one, sometimes it's useful. So it's good to speak of them just once, or maybe more than once. So if you have a sum starting from 0 to infinity in absolute value, an, converges. So if this sum converges, so think about the absolute convergence from calculus. If a series converges in absolute value, that means the series will converge absolutely, right? Without the absolute value, because it converges in absolute value. So if the sum converges in absolute value, that means we say the sum, the original sum, n equals 0 to infinity an, is absolute convergent. So absolutely convergent. Okay, so this was a property that's also taken from calculus, mentioning absolute convergence. And then sometime I think you guys also talked about conditional convergent, right? So that convergent doesn't converge in absolute value. It's conditionally convergent. Okay. So in absolute value, it might diverge. So that's from the past. We're not gonna deal with that. So this is just in general for any series. Now, what makes power series special, right? So we want to talk about power series. So what is a power series? That's the big question. So what is a power series? Those are the one we're after, right? Okay, we got some properties down, we got the definition, we know we have infinite sum, we also have finite sum. Now, what are power series? That's the next question. So let me give you the definition and then I'll explain. So, definition. So, a power series is a series of the form. So it has a very specific form. Of the form, this as follows. The sum starting at n equals 0 to infinity. So it's an infinite sum. An x minus x naught to the power n, right? So that's the special form of a power series, where so the power series is a series of the form this, and this series is centered. It's centered at x naught. Okay, so the point x naught that you see in the parentheses, that's the point of centered. Okay, so you can center your power series anywhere you want. We like to center at 0. Okay, so for convenient for this course, we would center, so we would like x naught to be 1. So we like x naught to be 1, meaning we center the power series at 0. So that means we will have the following form. So we have this form, the infinite sum starting at n equals 0 to infinity. We have an x minus 0 to the nth power. And if I were to just rewrite it nicely, which will give us a very beautiful form, we have n equals 0 to infinity, an x to the n. That's pretty. And we're going to assume in the future, so I'm very excited to get there, 5.2, we're going to assume that our solution form is a power series. So we'll use the infinite sum an x to the n centering at 0. Okay, so that's where we're headed. So right now we just want to kind of put this down. Now let's talk about its convergence. Okay, so I'm going to tag this into the second property that I just mentioned above. If the series convergent in absolute value, then we said that in the original series converged absolutely. Okay, so using that remark, or property number 2, let's remark this. So we're going to say this sum n equals 0 to infinity an x minus x naught to the n power converges absolutely if it converges in absolute value. So if the sum starting from n equals 0 to infinity an x minus x naught to the n converges. So if it converges in absolute value, we say the original series converges absolutely. Okay. Now, if you recall from calculus again, what was one test that you applied to test for convergent, absolute convergent? Do you guys remember? Does it ring a bell? So limits, right? So we're going to take some limits, but specifically, we're going to take a limit of a specific expression. So we're going to use the ratio test. Do you guys remember that ratio test? E. Yeah, so we're going to be using the ratio test to determine if it converges absolutely, right? So, Sadia, it's okay. We're getting there. So, I'll give you guys examples so that way you don't feel scared by looking at series. I think series are fun, but some 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 people don't like series. I don't know why, but I think they're fun. They're okay. They just look scary a little, but we can work with them, so it's okay. We're gonna go through some examples. Hopefully, it will make sense. If not, then we can go over some textbook questions. If you guys are comfortable doing series. So let's take over convergence a little bit, okay? So here are the three ways a power series can converge. Okay, so for convergence, so let me give you the info first and then we'll do examples. That way, I think it'll make a little bit more sense. So for convergence, there are three possibilities. So I like to think of it, there are three possibilities for convergence, okay? So some textbook might state it a little bit differently, but the idea is the same. So one, we can have the series converge only for x equals x naught, so just a single point. So the series converges only for x equals x naught, okay? And then we can also have it converges for all value for x. So meaning it converges for the entire real line. So we can have the series converges for all x. Do you guys know an example of a such function that converges everywhere? What's one function that you can differentiate as many times as you want? E to the x, right? The famous e to the x. Never forget e to the x. So here, e to the x. This converges everywhere. So if you were to express this as a power series, which we will do in the future, but just to give you a heads up, this is the sum, the infinite sum, starting from 0 to infinity, x to the n over n factorial. This series converges everywhere. We also have sine and cosine. They're also nice. They also converge everywhere. So sine and cosine can also be an example of the second case. What about the third one? Third one will be it converges only on an interval. Okay, so only on some interval. Okay, so say you have x minus x naught in absolute value less than r. That's when it's going to converge. Okay, so this should remind you of geometric series. Okay, geometric series will converge as long as what? So if you have the geometric series, say n equals 0, so example, to infinity, x to the n, right? That's a geometric series. This is equal to 1 over 1 minus x. And this will converge as long as x is less than 1. Okay? So that's when this is going to converge. If it's greater than 1, well, might diverge, right? So we want to talk about an absolute value x is less than 1 so that we have convergent. So now let's talk about the radius of convergence. So because it converges in some interval, that means we can actually find its radius of convergence. So let's do that. So let R be the radius of convergence. So actually I'm going to change the notation just a little bit so that we can match it up with the textbook. So the textbook uses rho as the radius of convergence instead of R. So we're going to let R, which is, we're going to call it rho later on, is the radius of convergence. Okay, so to abbreviate, this will be ROC. Okay, and the interval in which the power series converges is called the interval of convergence. So we're going to say, so the interval on which the power series converges is called the interval of convergence. So we're going to abbreviate that with IOC, interval of convergence. And how do we find these? Well, we're going to find these by applying ratio test. So we will use ratio test to find radius of convergence and interval of convergence. So that's the key. We're going to be using this test to compute what is ROC and what is IOC. Okay. So how does the ratio test works? How does this work? So here's how the ratio test works. So the ratio test is you take the limit as n goes to infinity in absolute value a sub n plus 1 over a sub n, and we call this to be some limit L. Okay, so we get some value L. This limit happens to be some finite number. Now, what are some cases can you have? Well, one, if L is less than 1, we know that the original series, n equals 0 to infinity an, is absolute convergent. Okay, so that's from geometric series, as long as in absolute value you're less than 1. Now, second scenario we can have if L is greater than 1. What if L is greater than 1? What can we say about the sum? We can say that the sum n equals 0 to infinity an is divergent. So we don't want that to happen. And the third scenario we know from ratio test is that if L is equal to 1, what can we say on that? Well, then it's inconclusive. We don't know anything about that series, so we would say then it's inconclusive. Okay, so we're heading toward L to be less than 1 in absolute value so that we have convergent. And that convergence, we're going to find the interval of convergence, and if we take half of the interval, we have the radius of convergence. Okay, so let me start you off with an example, and we'll finish the example next time I see you, which is tomorrow. Tomorrow. So here's the first example. Determine the radius of convergence, so ROC, of the summation. So let's do this one. So let's do n starting from 0 to infinity of x plus 1 to the n power over n times 2 to the n. So hopefully this notation makes sense. But so we have the summation n equals 0 to infinity of x plus 1 to the n over n times 2 to the n power. Okay, so we're going to pick up from here tomorrow. So any questions? Okay, so any questions, guys? Okay, are you guys doing okay? All right, so I'm going to go ahead and stop our session for today. Let me know if you guys have any questions.